In the previous lecture, we discussed about some techniques through which the matching of complex loads could be done, and one of those techniques was to make use of L networks, that is to say, networks in the shape of an L by making use of reactive elements such as inductors and capacitors. So, having said that, there is no reason to assume that those LC based impedance matching networks can be used only for complex loads. So, the point which I am trying to make over here is that these techniques can be used even for real or resistive loads. So, suppose I have a Smith chart over here. This is the center of the Smith chart. Now let us suppose I have a load impedance over here. This is ZL. So if I want to do the matching of this normalized load impedance small ZL to the center point, if I need to find a path by making use of LC networks, what I can do, I can essentially use the constant resistance circle that this impedance is a part of. So we can do this until, or we can move along from this point, let us say up, until the point where we reach the position where the real part of the conductance, the normalized conductance, is real. So therefore we can effectively move along over here until we reach here, which is the Z prime. After that we can come over here, which is nothing but the Y prime, and after that we can move along this trajectory to the center. So effectively, if the load impedance is real, which means it is nothing but a resistor, then moving upwards on a constant resistance circle first would mean that there is an inductor, and then we are switching over to the admittance coordinates and then moving up along the constant conductance circle, which means we are adding susceptance, thereby we are adding a capacitor. And whatever is the Z0 over here, that remains. So, it is necessary as an interesting activity to see that the load and matching network in this case is effectively an RLC circuit. So whether the frequency is low or the frequency is very, very high, the performance or the behavior of those resistors, inductors and capacitors don't change, at least not in theory. So as long as the components are identical, their behavior is what we expect them to have. So it is necessary to see or to revisit this concept of RLC circuits and see if something interesting can be done out using those. So RLC circuits are something that you would do in any basic electrical or electronics engineering courses, and therefore I am not going to spend too much of time behind them, but just give you a recap. So there are two kinds of RLC networks in common fashion. One is a series network, the other is a parallel network. So this is the R, this is the L, and this is the C in case of a parallel RLC. A series RLC would look something like this. So let us say the impedance looking into each of these networks is some Z. So obviously, as you know, in case of a parallel RLC network, the Z would be a parallel combination of each of these. And in the case of series RLC, the net impedance would be the algebraic sum of all of these. So effectively, what this looks like is something of this kind: 1 upon 1 by R plus 1 by j omega L plus j omega C. In the series case, it is something like R plus j omega L plus 1 by j omega C. And whether it's a series network or a parallel network, there exists something called as the resonance phenomena. And that happens at the angular frequency called omega 0, which is nothing but 1 by under root of LC. This is the case for both series as well as parallel networks. So over here, resonance effectively means a point or the frequency at which the impedance of the circuit essentially becomes purely resistive. The impedance of the circuit essentially becomes purely resistive. And in resonance, we also talk about a quantity called as quality factor. So the quality factor is defined as a ratio of the peak energy that the circuit can store at resonance divided by the average power that is dissipated. I'm sorry, the peak power that it can store at resonance divided by the average power that is dissipated. So in case of a parallel RLC network, so I'll say Q in case of the parallel RLC network, it looks something like this. It is R divided by under root of L by C. So larger the resistance, more will be the Q. And in case of a series RLC network, it's just the opposite. So in series case, for the resonance to be very, very strong, for the Q to be very, very high, you need the R as low as possible. So in other words, this can be written as I think this is the correct. Yes. This can also be written as something like this. And you can write in terms of the capacitor also. So now the Q of any circuit has a very important result, or it has a very important manifestation, and that is the bandwidth. The bandwidth. So the bandwidth of the circuit is essentially defined in this manner: F0 by Q, where F0 is omega 0 by 2 pi, which is the resonance frequency. So over here, one thing we can say is that higher the Q, lower will be the bandwidth. Higher the Q, lower will be the bandwidth. That means stronger is the resonance, stronger is the resonance, the less of a bandwidth the circuit can provide. And weaker the resonance, more is the bandwidth. So on one side, you have the concept of Q, and on the other side, you have the concept of bandwidth. Q is a measure of the energy stored versus the energy dissipated in the circuit. Whereas bandwidth tells you the range of frequencies over which your circuit can operate. So on one hand, we would like to make all our RF circuits as low loss or as lossless as possible. So therefore our Q must be high. But then in that case, we have to compromise on the bandwidth. And on the other hand, if we want an RF communication system or any other RF system that is working for a large, or that has to work for a large bandwidth, then in that case, the Q has to be low. So therefore, this is a classic trade-off. So in other words, more the loss, more is the bandwidth. More the loss, more is the bandwidth. So you can work this out for yourself. So what we have seen so far is the concept of series and parallel RLC networks, which all of you are familiar with since your basic electrical engineering courses. Now the question is whether it's a series network or a parallel RLC network, they both exhibit the phenomena of resonance. Resonance happens in both. So at resonance, that is the point where the circuit is storing the most amount of energy. Therefore, the question is that even though these series and parallel RLC networks are there, their impedance expressions are different, their Q expressions are different, but they have some very common properties that go hand in hand, in particular of the Q and the bandwidth. So therefore, the question is, can these networks be interrelated, or can these networks be transformed into one another? Can we transform a series network into a parallel network, or a parallel network into a series network? Well, the answer is no, we cannot. And why not? Because as we said, in case of a parallel RLC and in case of a series RLC, the net impedance is nothing but 1 by this, and in case of a series RLC, it is R plus j omega L plus 1 by j omega C. So in case of the parallel RLC, at DC condition, that is when omega is 0, what happens? When omega becomes equal to 0, this term vanishes, this term becomes infinite. So irrespective of the value of r, the value of z tends to 0. And at DC, over here, this term vanishes and this term tends to infinity. So over here, when omega is 0, the z tends to infinity. So at DC condition, they are both definitely not matching. And let us say, when omega tends to infinity, then what happens? So if omega tends to infinity, this term vanishes. You have 1 by 0. I'm sorry, you have 1 by infinity, which is 0. So again, the z tends to 0. And in case of a series RLC network, when the omega tends to infinity, the z will again tend to infinity. So therefore, it looks something like this. If I say, let us say z versus omega. So the parallel network will look something like this. And the series network will look something like this. So therefore, at 0 and at infinity, we see that they are largely varying. But the question is, what is happening here? Here is the point where the resonance happens. So therefore, at resonance, when omega becomes equal to omega 0, what is the impedance of the parallel RLC? When omega becomes equal to omega 0, these two terms essentially cancel out and the z becomes equal to r. Likewise over here, during resonance, these two terms would cancel out and the z becomes r. So therefore, if we keep the r values as the same, what we can do is we can actually have these two curves touching each other at that point of resonance. And the value of that is r and this is omega 0. So therefore, something tells us that this is the only interesting point at which we can say that the series and the parallel RLC networks are effectively very similar to each other, because their impedance essentially converges to R. So therefore, the question is, at the resonance frequency, it is often useful to interchange the RLC network from a series into a parallel one. Okay, so therefore what happens is, if we have an impedance matching network, it will definitely have a resonance frequency. It will definitely have a resonance frequency. So at that very resonance frequency, it can be realized using a different network as well, connected in a different fashion. So therefore, it is very useful and an interesting activity to see if these networks can be transformed from a series network into a parallel network. However, this series and parallel networks essentially consist of three components: the R, the L and the C. So therefore, what we will do, let us look at any two at a time. Let us first look at R and L. Let us make our life simpler by reducing one variable and keeping that as fixed. This is pretty much the simplest possible approach that we can have. Suppose we have a parallel network and we have a series network. So parallel RL network essentially looks like this. let's call it as LP for parallel, and RP as the resistor which is in the parallel network. And let us say that the series network looks like this: LS and RS. The question therefore is, can we correlate these two? As you know, the correlation can only happen at resonance. And for resonance, merely having R and L is not enough. We need a C also. So therefore, let us assume that we have a capacitor which is implicit. Let's call this as some dummy capacitor. Let's call this as CP. And when this network gets transformed, the terminals of the capacitor does not change. It is still here. And its value also does not change. That is the effective meaning of transforming only the R and the L. This is what we want to achieve to correlate these two at resonance. So therefore, for the parallel circuit, what will be the Q? The Q will be RP divided by under root of LP by CP, as we had discussed. And the resonance frequency omega 0 is nothing but 1 by under root of LP CP. Now, we have to essentially see that what is the impedance that is seen by the capacitor. So let's say ZP is the impedance seen by capacitor. That is the parallel combination of RP and CP. That is 1 by RP plus 1 by j omega LP. Right? So the question is, can we do something to sort of write this as real and imaginary parts separately? So therefore, let's do that. So if we write it this way, so since we are talking at resonance, let's call this as omega 0. We are doing the arithmetic at resonance. So this is what it would look like, where the numerator would go something like this. So to split this up as a algebraic sum of a real and an imaginary number, one thing that we can do is we can rationalize this. So therefore, this would look something like this. If we rationalize, the numerator will become this times RP minus j omega 0 LP divided by RP plus j omega 0 LP. And this would then give us the ZP as one thing I forgot, that is to multiply this also. Yes. So that would give us then j omega 0 RP LP square of RP. So we have a minus j and the plus j being multiplied. So this will become plus 1, and we will then have omega 0 squared times Rp times Lp square divided by Rp square plus omega 0 Lp the whole square. So now let us write the real part first. Let us say that I keep only the Rp in the numerator for this term, and this omega 0 square term and Lp square term I am taking as common. And over here in the imaginary part, let's take out j omega 0 from here, and let's keep Lp in the numerator and keep Rp square separately. Now for this first term, let us divide both numerator and denominator by omega 0 Lp square, and over here let's divide the numerator and denominator both by Rp square. So therefore this gives us, if we divide by this quantity omega 0 Lp square, the numerator will stay as Rp and the denominator will be 1. This will become 1 plus Rp by omega 0 Lp the whole square. Whereas this quantity, if we divide both by Rp square, this will vanish, and this will become 1, and we will get omega 0 Lp divided by Rp the whole square. So we have got this thing. Now what? What is this quantity? This quantity Rp divided by omega 0 Lp is nothing but the Q of the parallel network, as we have discussed. It is nothing but the Q of the parallel network. So therefore I can write this is equal to Rp divided by 1 plus Q square, and this is 1 by Q. So this becomes j omega 0 Lp divided by 1 plus 1 by Q square. So this becomes Rp plus j omega 0 Lp Q square divided by 1 plus Q square. So what we have done over here is we have effectively represented the impedance of the parallel RL network seen by the CP capacitor in the form of a sum of a resistor and a capacitor and an inductor. So this is the real part, means this is a resistor, and this imaginary part means j omega something, it's an inductor. So therefore, if I were to now correlate this with this quantity, it is like saying this is nothing but at resonance the CP capacitor should still see the same impedance ZB. So this is nothing but Rs plus j omega 0 Ls at resonance. So the real part is this and the imaginary part is this. So that means what we can say is that the series resistance corresponding to Rp is Rp divided by 1 plus Q square, and the series inductance is effectively Lp Q square divided by 1 plus Q square. One sanity check that you can immediately do is whether you are correct or not. You can verify that very easily by finding out the Q of the series network. The Q of the series network is nothing but omega 0 Ls divided by Rs. And what is that? Omega 0 Lp Q square by Rp. Yes, I think that is the correct one. And what is this quantity? Omega 0 Lp divided by Rp. This is nothing but 1 by Q of the parallel network. So what this means is the Q of the series network and the parallel network are one and the same. You can check it the other way around also. So Q of a series network, what we had proved, is Ls by Cp divided by Rs, because Cp does not change. And Q of a parallel network is Rp divided by under root of Lp by Cp. You can effectively prove that they will come out to be the same, that is Q. So this is a very good sanity check. And since we are talking of making the series network and the parallel network being able to transform to each other only at resonance, it can be done only at a single frequency, and that is F0 or omega 0. Now, suppose we say, suppose there is a strong resonance. Suppose there is a strong resonance. That means the Q is very, very high. In that case, what we can see is that the Rs will be much, much less than Rp. But if Q is high, you will see because of this square term, Ls will be almost equal to Lp. This is another sanity check. This is very, very important. So let us now extend this in a way that we transformed a parallel RL network into a series RL network. Likewise, you can transform a series RL network also to a parallel RL network. Likewise, you can transform between RC networks also. But in that case, you will have to place a dummy inductor. So, for your convenience, I am writing those expressions over here. So, first is parallel RL to series RL. So, that we saw is Rs equals Rp divided by 1 plus Q square, and Ls equals Lp Q square divided by 1 plus Q square. Second is the opposite, series RL to parallel RL. And that is just the opposite. So in that case, Rp will be equal to Rs times 1 plus Q square and LP will be equal to LS 1 plus Q square by Q square. So in both of these cases, you need a dummy capacitor. Next, parallel RC to series RC, and the opposite, series RC to parallel RC. So over here you will get RS equals RP by 1 plus Q square, that does not change, and CS will be equal to CP 1 plus Q square by Q square. Over here you will get RP is RS times 1 plus Q square, and CP is equal to CS times Q square divided by 1 plus Q square. In both cases, you need dummy inductor. You can prove 2, 3 and 4 by yourself. The first case we already proved. So in a similar way, you can proceed and complete the proof all by yourself. Now let us see whether the concept of a transmission line as an impedance transformer for matching, can it be done using lump elements? Now let us say we talk of impedance matching, but in a slightly different way. Suppose we have a source and a load. Suppose we have a source which is an RF source that has an internal impedance RS, and that is to be connected to a load impedance which is also real. Let's call it as RL. So now, one way to ensure maximum power transfer between the source and the load would be to have them as the same. So if that is not possible, one thing that we can do is to have a quarter wave transformer, where it converts this impedance RL into something that looks exactly like RS. Thereby, it will cause the maximum amount of power transfer to happen to the load. So while this QWT is very good, as we saw, it is not good for applications where the area is at a premium, or the length required or the size of the circuit has to be really, really small. Then in that case, as you know, the length of this line is lambda by 4. So then that would consume a lot of space. Therefore, we will be in a bit of a tricky situation where this will be a little difficult. So therefore, the question is, can we do something to realize the task of a QWT or an impedance transformer in a different way? We just now saw the concept of RLC networks. So then the question is, can we apply that? Can we apply that over here? So the QWT is effectively an impedance transformer. The QWT is effectively an impedance transformer. So the question now is, can I use a literal transformer in the place of the QWT? A transformer that is otherwise used in power electronics to either step up or step down AC voltages. Let us look at this interesting premise. Suppose I say, since I've been using the word impedance transformer a lot, let us actually use a transformer. Let us say this is an n:1 transformer. That means some kind of a step down transformer, assuming that n may be more than 1. So suppose there is some current which is being drawn by the primary winding. That is some IP, and there's some current in the secondary winding. Let's call it as IS. So IP, primary winding current. Don't confuse this as series and parallel. It may look the same because of the suffixes. Secondary winding current. So suppose now I define the impedance looking into the transformer as Zn. The voltage across the primary is Vp and the voltage across the secondary is Vs. So what we want, that the transformer should act in such a way that the Zin is exactly equal to Rs. So Zin is essentially nothing but Vp by Ip of the transformer, and that should be equal to Rs. This is needed for matching. So now by the transformer equation we can say that Vp by Vs is actually N. That is how the two are related. Let us say the load voltage is some VL, which is also equal to Vp. which is equal to Vs, because they are parallel. So then using this transformer equation, we can say that the load voltage VL, which is also equal to Vs, that is Vp by N. So on the other hand, for the current, we can say that the secondary current is N times the primary current. So therefore, if you put this over here, we can say that the load voltage is essentially IP times R this is a small mistake. So the Vp is nothing but IP times Rs. and we have this N. And this IP we can write as IS by N. So therefore, this becomes IS times RS divided by N square. And IS times RS is nothing but the load voltage. IS times, oh no, this is IS times RL is the load voltage. So I'm making a lot of mistakes, just be a little careful. So let's leave it as it is, whereas this VL is IS times RL, and that is equal to IS RS divided by N square. So IS and IS gets cancelled, and I can say that N square is equal to RS by RL. So that means if I have a transformer that works at RF frequencies, all we need is a turn ratio of this. All we need is a turn ratio of this. So therefore, if we are looking for a step down transformer, this will work only if RS is more than RL. Works only if RS is more than RL, because we are looking at a step down transformer. So therefore this ratio has to be more than 1. So the point is, even if we can ensure RS is more than RL, the value of N need not always be an integer. So when we are designing an actual transformer for power electronics applications, we try to have the windings as an integer ratio. But this may not happen. So therefore, also in practice, if we were to use a transformer, most transformers have some kind of loss. Even though ideal transformers are lossless, most transformers do have some loss, like eddy current loss or core losses. So therefore, what happens is, if we want to make our circuits compact, we have to be extra careful to design our transformer in such a way that the losses are minimized. So therefore, it is interesting to see how this particular transformer can be realized using some kind of a reactive network to achieve the same functionality, and that we shall see in the forthcoming lecture. Thank you.